Okay, so question 1 is the atomic structure question. It's usually one of the easier questions on the paper, so if you know this stuff well enough, it should get you off to a good start. First of all then, all it wants you to do is to tell you what's the difference between an atom of rubidium-85 and an atom of rubidium-87, and the answer is simply that rubidium-87 has 2 more neutrons. Just make sure that you're specific enough there. Don't just say different number of neutrons or more neutrons or something sort of slightly vague. 2 more neutrons it needs. Then we want definition of relative atomic mass. You know what I'm going to say about definitions. You've got to learn them properly, word for word, in advance if you can, because if you try and make them up on the day, it usually doesn't work. So in this case what we need is the average mass of an atom of an element on a scale where an atom of carbon-12 has a mass of 12. It's quite complicated. Important things that have got to be in there is you've got to have the word average, because remember what we're talking about here is a weighted mean kind of average of the masses of the different isotopes that occur in nature. So that's average is important. You've got to say it's mass of an atom, so that word atom has to be in there, and then all the carbon-12 stuff as well. 3 marks notice, so very important to learn the definitions because they carry a surprisingly big chunk of the marks on this paper. Next, the calculation. Again, this is a set piece. If you practice doing these atomic mass calculations, they're really very easy. So what you do is for each isotope you take its mass number, which numerically is the same as the relative isotopic mass. So they've given it here as relative isotopic mass, but it's the same number, so we've got 85, and you multiply it by how much of it there is. So 72.15% is the amount in this case. And then you add the same for the next isotope. So we've got 87 times 27.85 is the percentage of that one. And if there were more isotopes, you'd add those on as well. And then you divide by the sum of the amounts, which, because it's a percentage, is just dividing by 100 in this case. But if it wasn't given as percentages, if they were just relative amounts, you'd add up those relative amounts and divide by the total. So your calculator will tell you that the answer to that question is 85.557. But if you've read the question carefully, and the point is you must always, in every numerical question, look for this, it tells you you've got to round your answer to 2 decimal places. So every time you get a number crunching question, scan it carefully, look to see, does it say round off to a certain number of decimal places or a certain number of significant figures. You do not want to lose those easy marks by just missing that. So in this case 2 decimal places means we have to lose the 3rd one, and be careful when you're rounding. You don't just lose the 3rd one. You can see here that because that last number is greater than or equal to 5, that we've got to round upwards. So the 7 disappears and that number rounds up to a 6. It's important also to check that your answer makes sense. So that average is between 85 and 87, which it should be, and it's closer to 85 because you've got mostly 85, so it makes sense. Always double check that your calculator hasn't done something really silly and given you a number that can't possibly be true. Okay, so that's the answer to that one. Then it's asking you about the shape of a 5s orbital. Now, you've probably drawn 5s, or at least s orbitals, a number of times, and you normally draw them like that. But remember, that's a 2-dimensional representation of a shape which is really a 3-dimensional volume. Remember, an orbital is a region of space where up to 2 electrons of opposite spin can be located. So it's not a circle, it's a sphere. That's the answer, that's all you need, a sphere. Similarly, if you had a question about p orbitals, again, you're used to drawing them as figure of 8, but remember that they're 3-dimensional, so the shape is usually described as a dumbbell shape. Okay, on to the next part. So now we're on to ionization energies. This is a little bit trickier. It takes more getting into, more getting your head around, but once you've done it, again, it's quite predictable. There's not that many different questions that they're going to ask you, so if you prepare well for it, you can easily get the marks on this kind of stuff. First of all, it wants an equation for the second ionization energy of strontium. So what we're going to have to remember about ionization energies is that they're about losing one electron at a time. So the second ionization energy happens when the first electron has already gone. So our starting point is SR plus. Okay, the positive charge meaning it's already lost one electron. And again, notice in the question it says include state symbols. Once again, every time you have a question which asks you to write an equation of some kind, you need to check the question and say, does it want state symbols? Because again, it's a silly mark to throw away. So yes, this one does, and the state symbol it wants is gas. A lot of people tend to get that one wrong because they think, oh, strontium, that's a metal, that means it's a solid. Yeah, it is normally, but we're not talking about normally here, we're talking about when you measure the ionization energy, and in that case the definition requires, in this case, a mole of gaseous 1+ ions. So you have to vaporize it first. So ionization energy equations, it's always gaseous. And the second ionization means it loses another electron, so it turns into strontium 2+. Again, it needs that state symbol, still in the gas phase, and there's the extra electron that it's now lost. Now, the next one is the trend question, and the point is that they tend not to just say what's the trend in ionization energies across a period or something. They'll give you usually a sort of for instance, as they do here. So you've just got to check in your periodic table, make sure you know what you're talking about. So here, strontium and rubidium are both in the 5th period of the table. So we're talking about trend across a period. And what's hugely important is that you have this kind of checklist in your mind of all the things you need to mention when you're comparing ionization energies. So before we do this one, let's just remind you what the checklist is. So first of all, you've got to mention nuclear charge. That means the number of protons in the nucleus, the number of positively charged protons in the nucleus. And that matters, of course, because it's their positive charge that attracts the electrons. The bigger that positive charge, the more strongly the electrons will be attracted. So that needs to be mentioned. You need to talk about how many shells of electrons there are in the atom. Not just how many electrons, specifically how many shells, because that's what makes the difference. And it makes the difference to two things. To the distance from the nucleus of the outermost electrons. So that needs to be mentioned. Distance can also be affected by nuclear charge, so that one relates to both of these, because remember, if the nuclear charge increases, it will tend to pull them in closer. If you increase the number of shells, move them further away from the nucleus, so the distance is increasing. But the other thing that also depends on the number of shells is the shielding. And shielding is repulsion of the outer shell electrons by electrons in inner shells. So again, the more inner shells you've got, the bigger that term is, and that weakens attraction to the nucleus. So those are all the major factors, and what they all affect is attraction to the nucleus. And it's really important that you mention that you explain why all these things matter for the ionization energy, because they affect the attraction to the nucleus, and that is what determines what the ionization energy will be. That's what tends to get missed out. So make sure you mention attraction to the nucleus. Okay, so how does that work in this question? Well, rubidium and then strontium are adjacent in the 5th period. So strontium has a higher nuclear charge because its atomic number is 1 more, so it has 1 more proton. Strontium has a higher nuclear charge. That affects the distance. It pulls the electrons in closer to the nucleus. You need to say that. Shells, well, they've got the same number of shells. The outermost electrons are in the same shell. And that means that the shielding doesn't change very much. Okay, that needs to be said too. So you put all those ideas together, and the overall consequence is that the attraction to the nucleus is greater for strontium, and therefore it has a higher ionization energy. So you can see we've covered all of those things. High nuclear charge in strontium pulls the electrons in closer, same outer shell, so similar shielding, attraction to the nucleus is greater in strontium. You get all that down, 3 marks, bang, in the bank. Now the second one is slightly trickier, because now we're talking about second ionization energies, and you have to think a little bit about why now the trend is reversed, about why rubidium has a higher second ionization energy than strontium. And the important thing here is to think about what they have in their outer shells. So for rubidium, we've got all those inner shells, and then we've got 5s1. Okay, it's group 1, just has one electron in the outer shell. Strontium has all the same stuff, but then it has 5s2 because it's in group 2. And now you can hopefully see what's going to happen. That when we get to the second ionization energy, in the case of rubidium, that 5s electron has already gone, and so the second electron to be ionized has to come from the next shell down, has to come from 4p, in fact. Whereas, in the case of strontium, it's got 2 electrons in the 5th shell, so when one's gone, you've still got 1, and so the second ionization is going to come from there. And now you see the point. So again, go back to your checklist and say, well, strontium has the higher nuclear charge, but that's outweighed by the fact that the second electron, in the case of rubidium, has to be ionized from the 4th shell, whereas that for strontium has to be ionized for the 5th shell. And that means that the electron in the case of rubidium is closer to the nucleus and less shielded, and therefore more strongly attracted. So use all the same ideas, same checklist, and you can then explain it away. But you have to first of all make sure you think about the electron configuration. So when it's not first ionization energies you're comparing, you have to think a little bit harder. And that's the end of the question.